All right. So we're just going to kind of do some review today. I'll take questions from anybody that has kind of specific questions on the exam or on these practice exams. How are the homework? I mean, I can look through some that are similar. I think some of these might actually help on the practice exam with kind of similar setups as a lot of the ones in the homework. But yeah, we can work through whatever you have questions on. Just kind of start out. I might have, I think Monday, maybe I did, or I kind of in the past talked about possible short answers on the exam. So I kind of have a different idea for some things after the exam. So I changed some of the short answers into multiple choice. I actually think the way I did it, it's going to actually make those questions easier. So I've got it printed, but the exam has about 20 questions, all multiple choice. Kind of either get it right or you don't. So you don't have to show work. Obviously, hopefully you are doing work. I'll kind of have extra paper if you want some. Other than that, I would kind of say studying wise, kind of knowing those practice exams, if you feel pretty comfortable with those, I think you'll probably feel pretty comfortable with the exam. Looks pretty similar in terms of the kind of makeup and the content. I'll bring a formula sheet for everyone. So like when I hand them out, they'll have the exam, it'll have a formula sheet and kind of a scantron inside of it. Other than that, any questions? I think you showed a question earlier. Oh, it's not hand over here.
Oh, yeah, no, I was going to ask if your answer.
Oh, okay. Any other questions before we kind of start to introduce some material here? Okay, so I guess first I'll open up, are there any like specific questions or type of problem that someone would like to see me kind of work through? So today is not for me, it's for you guys. So to make the time most valuable, if you have questions, it would be beneficial for me to kind of go through something that I'm having trouble with. Nobody? Yeah.
Let's do something like Bayes theorem, because I've been having trouble with that.
Yeah, so we can work through another one like that. I'm trying to remember which one we did last class. Did we do the lie detector one last class? No? Okay, so we'll work through this one. So suppose we have kind of a lie detector setup where the outcome of the test is whatever the lie detector says, and the kind of true state of nature is someone actually is lying or they're not, right? So we're in practice exam A here. Problem 10. So what's the probability the person is lying and the test says they're telling the truth? So just starting out, what are we looking for? So the probability that someone is lying and, right, the lie detector test shows what they're telling the truth. So I'm just writing out the first thing, kind of the probability of what I'm looking for in problem 10. So I have this from, am I lying? And does the test say I'm telling the truth? So I'm looking for the intersection of two events. So before we go to the kind of what we're given here, how are we going to be able to solve this? If we go to our formula sheet, and anytime we're looking for the intersection of two events, I can find that using a conditional probability and multiply by the probability of the event I'm conditioning on. Right? So this isn't quite Bayes theorem, but it's going to set us up for a Bayes theorem problem. Okay. So, if this is my A, this is my B, I'm just going to write this kind of general version of the formula out. So what's the probability the lie detector test shows that someone's telling the truth? Given that they're lying, I'm going to multiply that by the probability of whatever I'm conditioning on. Okay. So I know the probabilities I need, at least for this problem. Now I'm going to have to go back, and I was kind of using this equation right here. Now I'm going to have to go back and see what I was given. So suppose that given someone is lying, so given that someone is lying, the probability that the lie detector test shows they're lying, so lie detector shows lying is what, 0.9. Is the first thing we're given. However, given that the individual is not lying, so given that someone is not lying, the probability of the lie detector test shows their lying is 20%. Right? So this kind of is a not a great lie detector test. And a lot of false positives. And the final thing we're given is suppose, studies find that on average, people are lying about 5% of the things they say. So the probability that someone's lying about something they're saying is 0.05. Well, so we can plug this one in right away. When we look here, and I don't have this probability, right? Given that someone's lying, what's the probability the lie detector test shows they're telling the truth? However, I should be able to come up with this missing component based off the information I was given. How can I do that? So I'm conditioning on the same state of nature here. Yeah, right? I'm conditioning on the same state of nature. Either the lie, if I'm someone who's actually lying, the lie detector test is either going to say I'm lying, or either going to say I'm lying, or it's going to say I'm telling the truth. Right? So these two probabilities have to add up to 1. When I'm conditioning on the same state of nature, but looking at the two different conditional probabilities for that outcome of the test, right? Either the lie detector shows truth or it shows lying. I know these have to add up to 1, so this probability up here has to be 0.1. Now, I could have found this ahead of time and kind of thought about, okay, if I condition on the same state of nature, when I'm looking for the other outcome of the test, I know these have to add up to 1. And down here, if I condition on that the person is not lying, right, but I'm looking at the other outcome of the test, that the lie detector test shows truth. I know that these have to add up to 1. So I would know that's 0.8. I don't need this for this problem, but if I, thinking about other questions I could ask. And then what's the other probability I know? Well, I know the probability that someone is lying is 0.05. What's the probability of the other state of nature that they're not lying? Well, I'm either lying or not lying about something. So 0.95. Questions for anything that I do? Yeah.
I'm just curious, like when you start the problem, I have troubles like picking which side of like the little line.
Okay, so anytime you see this word given, so notice here, given, well, except for I selected like half the paragraph. This part here, right? So anytime you see this word given, whatever you're told is given, right? It's kind of like saying, given that this is true. Right? So given that an individual is not lying. So whatever you're given, draw the line, and whatever you're given goes on the right-hand side. So and this is, in some of the word problems, like in the homework or things that we even worked in class, we didn't always use the terminology of given. Sometimes you can, I could have said here, however, if an individual is lying. Right? But, just to make it very clear on the test, I'll kind of use this common terminology, given this event. Right? So given that someone's not lying, and then it asks, what's the probability that the lie detector test shows that they are lying? You're told that's 0.2. Right? So anytime you see this word given, draw a line, and whatever you're given, put on the right-hand side. Is that kind of what you were asking?
Yeah.
Any other questions on that one? So it should be what? 0.005, right? 0.1 times 0.1 times 0.05 here. So that's how we would do kind of the intersection of two events. I won't kind of go through 11. It's basically a very similar setup. I think the only thing that changes is now I'm interested in what's the probability that someone's not lying. All right, and then kind of things all we have to do is update that state of nature. But to get to the original question of Bayes' theorem, we might have one right number is at 13 to 12. Right? So given that an individual fails the lie detector test, right? What is the probability that they're actually telling the truth? Right? Or they're not lying. So once again, this one, if I try to identify the probability of what I'm looking for, I have the word given, so I should probably think I'm going to be looking for a conditional probability. What am I given? It's that the individual has a lie detector test, they fail, right? I'll probably use a slightly better example on the exam, but I kind of even put in parentheses here. That's saying that the lie detector test is showing that the person is in fact lying. That's what the lie detector test is indicating. So given that that is true, what's the probability that they're actually telling the truth or that they're not lying? And you can use whatever shorthand you want. If you want to use the word truth here instead of not lying, that's fine, right? Whatever kind of makes the most sense to you. But this is the probability of what we're looking for. Any questions just on identifying that? So, like I said, usually exams are a similar format. Probably you can recognize we did something like this. We've got a word problem. We want to find a conditional probability. We're probably not going to be able to use that easier formula, which would be dividing two events here. That would be the intersection of the two divided by the probability of what I'm conditioning on. The problem is if I write this out in the context of my example, what's in my denominator here? Well, it's just the probability the lie detector test shows they're lying. I look over there, do I have that? No, I've only got the states of nature, right? The probability of the states of nature. And then I've got conditional probabilities, right? But I don't have just I have conditional probabilities for the outcomes of the test. But I don't just have the probability that for anyone at random that this lie detector test shows they're lying. So if I try to kind of use that easier formula, see, I can't do that, right? And so this is where we kind of made all those substitutions in the notes, right? So that if I don't have that denominator, if I substitute enough things in, I also have that the conditional probability can be solved for using Bayes' theorems or Bayes' equation, right? So I'm just going to write this out in the context of my example. Okay? So I've got this formula in front of me. I know the first step was identifying what I'm looking for. Second step is look at that general form of the equation. This is my state of nature. This is the outcome of the test I have. Right? The outcome of the test is that the lie detector shows they're lying. But I'm interested in the true state of nature being that they're not. So I'm just going to start writing this out in the context of mine. So the probability of S is that first thing. So the probability that someone's not lying times the probability of E. RE is that the lie detector test shows they're lying. Given S, the state of nature we were interested in was that the person is in fact not lying. Now we move on to the denominator. And if we notice is this first component of the denominator is the exact same thing as I had up there in the numerator. So I can just write this exact same thing out as that first component of my denominator. So what this represents, right? What this numerator, the first part of the denominator represents, are the intersection of those two things. The intersection of the outcome of the test and that state of nature. Now we can't really use this because we weren't given those intersections, although I believe in problems 10 and 11, that's actually what you're finding are these intersections. Right? So if you recognize that, you could use your answers from part 11 or 10 and 11 and kind of use this guy here. I probably wouldn't do that because you don't want to have cascading errors. Also, it's, I think, a little bit easier to kind of just, once you know the probability of what you're looking for, it's easier to just write this out in the context of our exam. So the second component we haven't filled in yet is what's the probability of S complement. So our S is not lying. What's our S complement? Yeah, that they in fact are lying times the probability of E, or that our outcome of the test that we were interested in was lie detector test shows lying. Given S complement, which we just said, is the probability of someone's lying. Now, if I look over there at the probabilities I was given in the original problem, like this one that said use this in the next 3 questions, the probability someone wasn't lying was 0.95. Probability somebody was lying is 0.05. Given that someone's not lying, the lie detector test incorrectly showed that they were 20% of the time, or that probability is 0.2. And that given someone's lying, what's the probability the test actually shows that they're lying? What was that? Was that 0.9 or was that? Yeah, it is 0.9. Let's see. Well, now I've got all the numbers of public answers from out of it, getting that entering on top of it. So, like I said, I'm kind of based off the format, probably be able to realize when you get to that problem that you're going to need to use Bayes' equation for. Right? And it's always when you're looking for a conditional probability. So anytime you have kind of that given, that we're given, you know you're looking for a conditional probability. identify the probability you're looking for, write it out in the context of your example, and then it's just a matter of plugging those probabilities you were given in that word problem that said, use this for the next however many questions, 2, 3. Any questions on that one? Or clarification on anything? All right. So I can't remember what types of problems we worked through last class. So if I start going through something and you guys don't want to see it, be free to let me know. Yeah.
So just making sure for the given part.
Yep.
So this one says given, you put the line and put
Right hand
what
side.
comes after,
Yep.
and then the opposite on the other side, basically.
Yeah, right. So it's like, whatever we're given, right? We're assuming this is true, right? So whatever's on the right hand side of that line, you're assuming that that we're in this world. So, for example, if I'm thinking about the probability it rains, right? But I'm giving you the fact that, well, given that you're in Seattle, now what's the probability it rains, right? Yeah. So whatever you're given is the event that you're saying, okay, I didn't have this information before, but now I do, right? Now with this additional information, now what's the probability of this other thing? And the other thing would be what's on the left-hand side. That's what you're actually looking for the probability of. Any other questions? All right. So any type of problem before I kind of just start picking and choosing ones to work through? Yeah.
Can you do something with like the union and intersection with like mutually exclusive and independent?
Oh, okay. Yeah. So I don't think we worked through this example last class. So we've got, I think I did the Republican. This is an easy example for me because it probably doesn't make sense. So let's say I had this contingency table, right? And this is a good question because I wrote the example, so I know it's on it. It's a good idea to know how to determine if something is mutually exclusive or if it's independent or both, right? We're kind of finding both those things. So the easy one should be what? I'm thinking about the two things of being mutually exclusive or independent. Which ones really should be a little bit easier to determine? Mutually exclusive, right? The definition of being mutually exclusive, the most easy way to think about it is that two things can't happen at the same time, right? So if two things can't happen at the same time, we know that the intersection of those two things will be, yeah, someone's holding it up, right? 0, right? Two things can't happen at the same time. The intersection, the overlap would be, well, it doesn't exist, right? So that probability is 0. So here, if I'm thinking about marijuana legalization and being older than 55, right? So the probability being older than 55 and wanting marijuana legalized, if that intersection is equal to 0, right? We would say these are mutually exclusive. If it's not equal to 0, then they're not mutually exclusive. That's as easy as it is. Right? So, and what the question would look like there is something like this, number 9. Right? So are they mutually exclusive? Well, if we look at this table and we go to the intersection of being older than 55 and wanting marijuana legalized, it's not the highest probability, it's 0.14, but that sure isn't 0, right? So because it's not 0, we would say no, they aren't mutually exclusive, or they're not mutually exclusive. So we go back down here, right? No, they're not mutually exclusive. And here, I think maybe, so I phrased the question a little bit differently, but it doesn't change what we're looking for, right? So actually here I'm asking if being younger than 55. So if that event O is being older than 55, I'm actually looking for the intersection of O complement. Right? But it doesn't change anything because I didn't have any zeros up there. If I go to look up being younger than 55 and wanting marijuana legalized, I don't have a 0 there either. So we would say that no, they're not mutually exclusive because that intersection, right, is not equal to 0. So one thing to kind of keep some of this straight, I don't think I did this with you guys. If I did, stop me before I was going too far into it. I think it'll help keep some of these symbols and things clear. So we kind of raise this. Yeah. Okay. I guess I can phrase the question the other way. Does anybody, still arrive and then I can wait for a response. So if I think about some of the words that I'll see here. So I've got and, or, and given. And we're thinking about this kind of this upside down set sign, right? Or it looks like an upside down U, or looks kind of like a U. It says for and, this is going to represent intersections. And the or kind of this upside, or this right side up set sign, is going to represent a union. And then we kind of already talked about givens today, but right, that's where we can use that conditional line. And that word given indicates we're looking for a conditional probability. Okay. So anytime I'm thinking about mutually exclusive, I'm thinking intersections, right? This and this, right? We're kind of this upside down U set sign. So when I'm even just looking through the answers, knowing something about the union doesn't really tell me necessarily that events are going to be mutually exclusive. Right? So I know that I should be looking for something where the intersection of two events is indicating something. So right away, I could rule out B and C because they're not even looking at intersections. Right? And that's what I need to be looking for mutually exclusive events. And then furthermore, we check to see if the intersection was 0. It wasn't, so we said they're not mutually exclusive, so we can then rule A out. So that would be kind of one way to kind of start canceling answers out until you're just left with one. But just the general idea of being mutually exclusive, are these two events, we have O complement and LM, are they mutually exclusive? Well, no, because the intersection of those two is not equal to 0. Any questions on that one before that? Yeah.
And you probably got some questions on whether or not it's mutually exclusive on the test, right?
Yeah, so yeah, for sure, you can expect to see something about two events being mutually exclusive, and you can expect to see something about two events being independent. Okay. So we think about the definition of independence. The kind of most general or the truest kind of definition is, if I'm looking at the probability of an event occurring, right, that if you then tell me, okay, I'm going to give you some additional information that B has already occurred. Now, what's the probability that A occurs? Right? So when we look at this conditional probability, we're still looking for whatever's on the left-hand side of that given line. That's the event we're still looking for the probability of. It's just we're now looking for the probability that that thing occurs given some additional information, right? So maybe I mentioned what's the probability it rains, and then what's the probability it rains given that I'm in Seattle. Right? That's kind of the idea. We're still looking for the probability of whatever's on that left-hand side. So this is the definition of it. These two things are equal. We would say these are independent events. Why are they independent? Because the probability of A isn't changing when you give me this additional information. So it must be that these two things aren't related, or they're independent from each other. Right? So that's one way to think about it. The word like independent, that they're not related to each other. Okay? So knowing that B has occurred doesn't change the probability of A at all. So we can check this using this table. So we're asked what? A is supporting national legalization and being 55 or older independent events. So here we've got, I could check to say, let me see how the answers are written. I'll actually show you, yeah, we'll do this one first. So let's say, I just write this out in the context of my example. So my event A is older than 55. My event, B is if they want national legalization marijuana. So I can get these from the table. I can't directly get my conditional probability, but I know that any conditional probability is the intersection of two events divided by what I'm conditioning on. So the intersection of these two events divided by whatever I'm conditioning on. And I can get those values from the table. So I go back. All right. What's the probability that someone is older than 55 and wants marijuana legalized? Say, hopefully we know how to read these. So it's older than 55 and what's marijuana legalized, right? So 0.14. What's the probability someone's marijuana legalized? Well, that just is in the total column, so 0.66. Which what, that works out to be roughly 0.4 something, or just under 0.4. Somebody else said, oh man, actually, I haven't got that for you. I was way off. I wasn't thinking about that. 0.21. Okay. So I know that this probability is 0.21. What's the probability of being older than 55? 0.25. I'll go to that total column on my table, right? Older than 55, yes. Go to the total, that's 0.25. Are these two probabilities equal to each other? They're close, but not quite equal. So because they're not equal to each other, we said that they are not independent, right? Or that they do depend on each other, or they are related. So if we find that those two things aren't equal to each other, those two probabilities, we would say they're not independent. Okay? So we know that these, yeah.
When just kind of looking at how the answers are written is, how do we know those first?
So it doesn't matter which way you try to check, right? So I think hopefully, I don't know if mine lined up here. So like which is on the left and which is on the right, it doesn't matter, right? Because I could rewrite this. Right, and just would flip those values, I'm still going to see that those two things aren't equal to each other. Right? So it doesn't matter which one I start. In terms of which one of these goes first, it also doesn't matter. So we just found that these are not independent events. Right? So no, they're not independent. We know right away from the A or B. Doesn't matter which order we use to check it, right? As long as we make sure that we're comparing the same or unconditional to the same event of the conditional probability, right? So whatever you have here that's unconditional, when you look at your conditional probability, it should be the thing that's on the left-hand side, right? Because you're still looking for the probability of being older than 55 because we have this given additional piece of information. So once I know that it's no, they can't be, they're not independent. Well, now it doesn't matter which way I check. I'm just looking to make sure, am I comparing the unconditional probability, the conditional probability to the unconditional probability of the same event, right? And here in this option, you can see I'm comparing the conditional probability of LM to the unconditional probability of O. It doesn't have to be anything, right? Now I could have I could have written the answers slightly different up there. So instead of looking at that conditional probability of O being equal to the unconditional probability of O, that's one way it shows me LM and O are independent. But I can just reverse the way I'm saying it. So now are LM and O independent, or O into LM independent? Well, if they're independent from each other, it doesn't matter which way I say it, right? So I could have also checked to see if the conditional probability of LM was equal to the unconditional probability of LM. So that's another way that the answer could have been displayed. But once again, what you're looking for there, doesn't matter which way you check it, you can determine that they're either independent or not independent events. And then it doesn't matter which way I display the answer. What you're looking for there is that some conditional probability is not equal to the unconditional probability of the same event. So I could have actually had this as answer A, right? And it still provides the same justification for why these two events aren't independent. So I guess the key is you're looking for something that compares whatever the unconditional probability is, whatever event it's looking at, you need to make sure that the conditional probability has that same event on the left-hand side. Right? Does that? Yeah. Now, usually, I probably would be a little bit nicer than I would in this question. Usually, I think the way you first read it, you would initially think putting LM on the left and O on the right, just because that was the order in which I wrote it in the problem. So usually what I'll try to make sure I do on the exams is whatever order I write it in, I usually show the answers in the same order, just because I know that when you read something, that's the first kind of way you'll go to do it. Any other questions on that one? All right. Any other questions or types of questions that someone wants to see worked through? So I'm gonna do one down here. I don't think we did this last class. I might throw in some additional problems here too. So let's say we've got the number of people struck by lightning in the US every year is approximately 3 people. What's the probability that less than 2 people are struck by lightning this year in the United States? So we've got kind of this average rate over a given time interval. What's the highest number of people I could see get struck by lightning? Well, I guess this one theoretically, when you think about would be the population of the US, but even if it's not truly infinite, we can think about if it's an insanely high number, right? We don't really know what that cap would be, we should be thinking about the sun. Right? We can't put a cap on the number of people get struck by lightning here. We're not looking for like, 2 out of 20 or 2 out of 100. We're just looking for the probability that we see 2 over this interval. Right? So we've got this Poisson distribution, which I'll show you where it's at in the formula sheet, but just so we have it as a reference, I don't have to run across the room. There's going to be something like this. So we've got the number of people struck every year is 3, and we want the probability of being what? Less than 2. So just write down what the probability we're looking for. So how can I find the probability that it's going to be less than 2? Well, this equation gives me the probability of being exactly equal to whatever x value I plug into. So what can I break this down into? What outcomes fit this criteria? 1 and 0, right? I'm okay with awkward silence, especially when it's something that I think, fifth graders might be able to tell me, right? What are the outcomes that fit? What's less than 2? 0 and 1, right? Especially when we look at these numbers of successes, they never go negative. You can't see something happen negative times. Either the lowest that ever occurs is 0, it just doesn't occur, right? So 0 and 1. Well, now it's just a matter of using that function, plugging in our x values. So lambda to the x times e to the negative lambda over x factorial. Notice with 0 and 1, things start to become pretty easy. 1 factorial is 1. 3 to the 1 power is just 3. Everything is a 1 power. And then I'll add to that lambda to the x, e to the negative lambda, x factorial. Well, 0 factorial is 1. Maybe the 0 power is 1. This becomes a little bit easier when we're dealing with these lower numbers of successes. Now, if I just think about before I even went to the, first of all, are there any questions on kind of what I just did here? So if I think about, sometimes if I look at the answers, I can rule a lot of them out right away, just thinking about what I'm looking for. So if the average number of people that usually get struck by lightning is 3, then we know that 3 should be the most likely outcome. As we look at numbers of successes further from that, the probability is declining. Right? So I'm looking for the probability of saying 0 and 1. I know those won't be the most likely outcome. In fact, I know that there's probably 3 outcomes that are more likely than either one of those. So if I'm thinking about what this probability has to be, right, I can kind of say, what if it was 0.85? If this probability was 0.85, or in fact, what if it was 0.541, right? So if it was C or D was the right answer, let's kind of rule this out by kind of using cross elimination. If that was the probability of being less than 2, why could I say that I know that that's wrong? Well, you would probably expect them to be a little bit smaller, but you know for sure they can't have a probability greater than 0.5. When you think about, if we split this in half, right? So each one's 0.5. 3 still has to be the most likely outcome, right? So if you're telling me that, saying 0 and 1 has a probability as high as 0.85, well, one of those outcomes would then have to be more likely than 3, just because we can only add up to 1, right? So an answer as high as 0.5 doesn't make sense. 0.5, maybe we can't really theoretically rule out, but it seems way too high given that the outcomes we're looking at doesn't even include the 3 most likely outcomes. And it only includes 2 out of, think about this right tail goes real far out, right? So if I'm looking at these values here, I'm thinking A or B makes a lot more sense, right? This probability is going to be a lot closer to 0 than it is going to be close to 1. Now, from there, best guess of A or B, I actually have to go through the work to figure out what that probability is. And I think if we do this, I think, if I remember right, this is probably around 0.149. This would be approximately 0.05. I'm probably off a little bit in either direction. Tell me how far off I am if you want. But, right, those 2 things should have to believe about. I think I'm wrong. Maybe it's 0.149. What's the answer that I have? Is it A? Yeah, okay. Yeah, so I think that they're roughly these probabilities. Questions on that? What if I asked you for the probability that X is greater than or equal to 2? And say we hadn't done this work already. Well, I could use that equation, plug in 2, then find that probability. Use that equation again where X is 3. Use that equation again where X is 4. But where do I stop, right? So what's an easier way of doing that? Right, go to the correct table. I don't want to go through everything. Yeah.
You would just find the 1 and 0 and do 1 minus those
Yeah,
two
right.
numbers.
I'm just gonna subtract 1 minus the complement of this event. So 1 minus the probability X is less than 2, which the only things that fit that criteria would be 0 and 1. So it'd be the same process what we just did. We would just find those probabilities, but then have to subtract them from 1, right? To get the probability that we were actually interested in. What if instead I ask you, what's the probability that one person is struck and killed by lightning this month? So we're going from a larger to a smaller time interval, right? Year to a month. So what am I going to have to do in order to find that probability? The average number of people killed every year is 3. The number of people on average killed every month would be
divided by 12.
Yeah, right. So if I want to find the average rate per month, I'll take the average rate for the year and divide it by 12, right? So anytime we want to go from a larger to a smaller time interval, we need to divide by some factor, right? Once again, it should be an easy factor, right? Years to months. Hopefully we know there's 12 months in a year. Right, so we get kind of the average rate on a month is 1/4. So now it just becomes, okay, my new lambda is 0.25, right, or 1/4. X that I'm looking for is 1, e to the negative lambda over x factorial, which our x was 1. So once we have that new lambda, it's really just like what we were doing before. Okay. Any questions on this one? So in a lot of these examples, you'll kind of notice I use some nice integer values like 3 and here. But when you make that conversion, sometimes more likely than not, you might end up with some new lambdas that aren't these nice integer values, right? So don't think that means they're wrong, right? Your average rate can be 1.3569, right? It can be any value, that average rate. It's just that the outcome you actually see, right, has to be an integer. Questions on this one here? All right. So what's another one I want to kind of like to do? Did we go over just like a general discrete random variable last class? Anyone remember? No. Yeah, we did. I thought we did. If it was me, I maybe wouldn't focus as much on a question like this. Wink, wink. Or we can kind of do something like this, kind of covering some old stuff, just to point out some things that you might want to make sure you're careful for on the exam. So hopefully, problem one, I'll tell you right now, problem one, calculating me. Actually, I shouldn't say that, I should look at the example. One of the first two problems you'll be asked to calculate in me, okay? Whatever question, I believe it's question one. I hope everybody gets question one right? I mean, calculating mean should be the easiest thing we've done, right? So here, if I want to find the mean for the age of these spiders, this is where, if I give you several variables, be really careful, right? Make sure you're looking at the right variable. Like if I ask you for the mean, okay, the mean weight. No, I'm asking for the mean age. So I look at this right away. What answers can I rule out? 178 is holy cow, right? Average age of 178 on a, I think UFC fighters or something, that doesn't make any sense, right? But there's another answer that doesn't make any sense either. 43.75. Why? Yeah, right. I'm looking for the average age. My youngest age is 28. My oldest age is 41. How can the middle part of the data then be outside of that range? It doesn't make any sense. So right away on question one, not only is it one of the easier questions that we can, calculation-wise, I've limited it down to two answers right away. I know it has to be 35 or 37. So from there, what am I doing? I'm simply adding all those values up, right? 28 plus 37 plus 37 plus 41 plus 32, and divided by the number of numbers I have. So don't get tripped up. If we look at this formula sheet, when we go back, we had a difference when we calculated the sample variance versus the population variance. That was where instead of dividing by n, we divided by n minus 1. When it comes to a population or a sample mean, we're always dividing by that kind of number of observations that we see n. Right? So there's one way you could mix it up. I think that's probably how you get to 43.75, maybe not. But if you divide by n minus 1, you're going to end up with kind of a larger value. Right? But you don't do that in the mean. You always divide by the number of observations. Okay? So hopefully everybody gets that one correct. The next question, which you'll have to do something similar in the exam as well, is what's the median weight of the above fighters, right? So if we want to do the median, you can kind of, this is where we're looking for that middle value. That kind of exactly splits the data, 50% observations above and below. We have an odd number data set here, so that's kind of nice, right? Because I know I'll be left with exactly one value in the middle. Now it's just a matter of crossing out the lowest, crossing out the highest, next lowest, next highest. You could do that on the table here. It might help, right? If you kind of write these out, because you can already notice I did not identify the lowest right away. Your eyes might just go to a specific value, right? But if I write these out from smallest to largest, it becomes a lot easier to figure out what that median is. Questions on this one? If I have 6 observations, and let's say I'm left with 2 values, and the median would just be, the average of the 2 values I'm left with. Right? It's the only additional step if we have an even numbered data set. Okay. But also a similar idea, if I'm looking for the median weight, I'm still looking for a middle value, right? Median and means are just different measures of where the middle point of the data is. So if I look at weight, it goes from 143 to 204, right? 71 and 73 don't make any sense at all here. Okay. So this next one, right? If I want to find the average, I want to eventually find the sample standard deviation. Well, in order to find a variance or a standard deviation, I'm going to need to find the mean. If I found the mean wrong, all bets are off. So I give you, right? If I tell you, the average height or the mean height of fighters is 71.6, what's the sample standard deviation height? Doesn't look like there's any off the face that we can rule out. Remember, if we saw a negative value here, we know we can rule that out because the variance and the standard deviation are always positive. But then we'll just use that mean. You could even create a column like right next here. I don't care if you write it in the exam. Look at that first height, 69. Subtract that mean of 71.6. Square that value. Then add to that the next observations, so 204, no, use the wrong variable, but 74. Subtract that mean of 71.6, square it. Basically do that for every single observation and add them all up, right? So you're getting the deviation of each one of those heights from the mean, squaring that value, and then adding them all up. Once we do that, what's the next step? Right, we're looking for a sample standard deviation. Wait, I need to do a little bit of work here while I'm waiting, so you can just blurt it out if you know it. What would the next step be? So not quite, right? If we have a discrete random variable, we didn't have to worry about dividing by anything. But here we're dealing with an original kind of where we started out, just a variable that's already been realized. So we go to that formula sheet. Once we add up all those deviations squared, we then need to divide by n minus 1, right? Because we have sample data. So whatever this total ends up being, I don't know if anybody's kind of working through this. If you find this, I was trying to do that real quick, right? You would divide it by n minus 1. We're here, we had 5 observations, so you'd be dividing by 4. Okay. So let's see if we can get this here real quick. So I got 74. What was the next height? Just so I can give you some numbers to check the intermediate values. So 73 plus 74 minus 71.6 squared plus 68 minus 71.6 squared. So unless I made an error, I was entering that kind of quickly on my calculator. That would be approximately 26.4. I then divide that by 4, and I get 6.61. Okay, so I'm done, right? What else do I need to do? If I'm looking for that sample standard deviation, it's not that 6.61, right? It'd be the square root of that. Okay. So I'm guessing square root of that, roughly that 2.58. I had some rounding errors, so I think that, some of the numbers I have up here, you might get 2 or 2.57. All right. Once again, even if you made some rounding errors, it's never going to be an answer, or you're kind of only off by that 100 decimal. So read these problems carefully when you get to the exam. Is it a population data set or is it a sample data set? If it was a population data set, I would have instead divided by just n, right? 5, right? Not n minus 1. It's only when we're looking at sample data. And then also be careful. Know if you're looking for the variance or the standard deviation. If you're looking for the variance, once you add these up and divide by n or n minus 1, depending on if you have sample or population data, well, then you're done. But if you're looking for the sample standard deviation or the population standard deviation, once you find that, you still need to take the square root of that variance. It might be a little off. Like I said, I did some rounding this, the first decimal, and probably when I calculated, I just kept all the decimals there. But roughly 2.58, 2.57, roughly 6.6 here, just something else. Any other questions for me? So, one thing I want to mention, sorry to do this again, but keep getting scheduled to these meetings I don't want to go to. I will be in my office a little bit later today, more so from like 2:50 to 3:50 instead of 2:30 to 3:30. So if you have some questions, you want to stop by there, I should be in my office a little bit later. Tomorrow, kind of usual office hours, 11 to 1. If you have any last minute questions, also if you want to meet outside that time, I've had a couple of people already reach out. I'll be around the majority of the day tomorrow, so feel free to send me an email. If you want to go over a couple of questions that you have leading to that exam. Otherwise, we're taking the exam in class on Friday. I'll try to get here a little bit early so we can all kind of get settled. The majority of us are here. We'll kind of get going a little bit early to give you just a little bit more time. Okay. All right. Well, good luck studying. I will see you guys on Friday.